Good morning, everyone, and welcome to this webinar. You can see my slides, right? Yeah. Okay. So I'm Pascal. I'm the EUPEX dissemination leader. And today we are going to talk about vectorization of FEM kernels. So that's the application ESPRESO FEM. So before we delve into today's topic, I wanted to say a few words about this webinar because it's one of a series that's organized by EUPEX to share our results and lessons learned. We organize monthly webinars, and we started with what is ready today. So with the applications that were analyzed and optimized under EUPEX, and we are also addressing some of the components of the EUPEX software stack. So the recordings of all of our webinars are available on our YouTube channel. So you can just go to YouTube, look for EUPEX, and you'll find us. And we have two new webinars scheduled, and I see there is a typo in one of them. But anyway, on the 9th of April, we will talk about Ocean, not Ocean, Ocean, which is CA's administrative software stack for HPC clusters. And on the 20th of May, we will talk about Parastation Modulo, and this will be presented by Partech. So the registration is open for those webinars. If you go to our EUPEX webinars page, the link there is here, you will find the web pages to register. Also, one important point, I will send the slides, today's slides, I will send them to you, to all attendees. So you will have them very soon. I will send them probably tomorrow. So now let's dive into today's topic. Today's topic is ESPRESO FEM. So that's one of the many applications examined and optimized under EUPEX. And I'm very happy to welcome today Andres Meka from IT for Innovation. Thank you for accepting to be our speaker today. Andrew holds a PhD degree in computer science from the Technical University of Ostrava. You know, that's the home of IT for Innovation. So welcome, and well, I will hand over to you. I will stop sharing so you can share your slides. Sorry. Yep.
Okay, thank you, Pascal, for introduction and for possibility to share my research in this this webinar. Do you see my slide?
Yes.
Okay, so I will start. My talk will be about the vectorization of FEM kernels. At the beginning of my talk, I briefly introduce what are the FEM kernels or the FEM assembler and SIMD instruction function, and then I will describe our approach for vectorization of these kernels. The approach is based on commonly known cross-element approach. And in our tool, we implement another optimization for adaptation the kernels for runtime conditions. And in the second part of my presentation, I present the result that were achieved with our approach. So what is finite element method? It is a numerical method for solving partial differential equations, and the input of the method is some representation of the model together with material description and initial boundary conditions and so on. model is usually represented by finite element mesh. It is just a set of nodes and elements where the elements represent the nodes connectivity, and both nodes and elements can be grouped into the regions, and these regions can be used for defining physical parameters such as material and so on. When we have the finite mesh, then in the FEM assembler we apply local matrix kernel for each element in order to compose the system. And in the solver, then we solve the system, and the solution of the system is, for example, distribution of the temperature or the bending, or the displacement of the beam, or some model. The input for the assembler is the element that is composed from the coordinates and physical parameters, and the output for each kernel is a matrix that is inserted then to the global sparse matrix. What are the challenges for achieve the best performance for such an assembler? From the optimization point of view, there is a rich set of element types with different number of nodes and Gauss points, so there is different number of loops that are needed to perform inside the assembler. There is also a rich set of physical parameters with different number of required operation. Some physical parameters allow to compute just the upper part of the matrices because of the symmetricity, or there are some physical parameters that contains a lot of zero values. So if we avoid this useless computation with the zeros, we can also get the better performance from our kernels. Also, for increasing the arithmetic intensity of each kernel, we should evaluate all parameters at once. It means if we load the coordinates from the element and so on, we should apply all boundary conditions and so on. And then if we compose the whole matrix, the element matrix, we should insert this matrix into the global system. It is also challenging from the parallelization point of view, because we should somehow avoid race condition when the local matrix is inserted to the global matrix. And in order to reach the best single node performance, we also should somehow implement vectorization in the form of intrinsic instruction that is called vectorization, and it is the main topic of my presentation today. So what are the SIMD instructions? Basically, if we have some array of doubles, and if we compute something with this double, in the case of SIMD instructions, we are able to perform the same computation with several doubles or floats and so at once. According to the particular instruction set, and according to the length of the registers, we are able to perform, for example, 4 computation at once with AVX2 instruction set. In the case of AVX 512, we are able to compute 8 computations with doubles simultaneously, and it means that we can theoretically reach n times speed up of our computation. Unfortunately, even for the code that is possible to vectorize, the vectorization is still very challenging, because it usually means to do something with our code, because despite the maturity of current compilers, auto-vectorization is not always optimal, as I show you later in my presentation. What is also very important, that this vectorization, put this SIMD instruction into your code, is essential to reach the peak performance. So it is very important to somehow do it if we want to get the best performance that we can. Because there are a lot of tools with that are able to compute FEM, that are used FEM methods for computation for physical simulations. There are a lot of papers that describe the way how the researchers optimize their tools for utilize this vectorization. Usually the vectorization is based on cross-element vectorization. In the case of our approach, we describe the approach in this paper, and we also we also adopt the cross-element vectorization, because this cross-element vectorization is very easy to write. And besides this cross-element vectorization, we also apply another approaches to improve the kernels even more. We also applied metaprogramming for utilization of compilers for building the kernels that are tailored for the particular set of parameters, for example, element type and so on. And because we want to have the kernels that are easy to write and also that can adapt for particular set of physical parameters, we experiment with dynamic selection of subkernels in the way that we divide the whole assembler into the several subparts, and then we experiment with runtime branching to adapt the kernel for particular set of physical parameters that are described by the user. Of course, this dynamic selection introduces some performance overhead, but as I will show in the measurement, this degradation of performance is small, and we believe that it is a good trade-off between the simplicity of writing efficient kernels and small performance degradation. So the main motivation for the dynamic behavior is because the real-world examples are typically composed of several regions. For example, this temperature sensor are composed from different parts with a different complexity of the assembler. And on the right side, we can see the assembler, the general assembler that can be used for the whole sensor. But if we look closer to some parts, there is possibility to assemble some parts with the much smaller assembler, and to assemble the matrices for some part more simply and quickly. So because the complexity of the assembler can be dependent on the physical parameters, we want to somehow utilize this knowledge for increasing the speed of the assembler. So I will start with the description of our approach. So typically, FEM kernels workflow is following. At the beginning, there is a loop for gathering coordinates of current element and other physical parameters such temperature or displacement. And then there is a loop across Gauss point that perform the integration, evaluation of physical parameters and assembling the contribution for to local element matrix. Then the local element matrix is inserted to the global matrix and the system is solved. In the case of matrix-free method, it is the method that solves the system by iterative method, and the inserting the local matrix to the global matrix is avoided, and the solution is substituted by the iterative method that compute matrix vector product in each iteration, and this matrix vector product is compute per element. So this method can save a lot of memory at the expense of the speed of the computation. And if, for example, we want to implement this matrix-free method, the speed of this method is highly dependent on the performance of the assembler. So it is very important to optimize the kernel. But even we use the standard approach with the global matrix explicitly assembled, the assembler can take a significant portion of the time. So the first part of our approach is cross-element vectorization. The idea is very simple because the idea is similar to idea of SIMD instruction. Instead of assembling the matrix with the single element only, we assemble more elements at once, according to the instruction set and according to the length of the vector register. We assemble, for example, 4 elements at once in the case of EUPEX2 and so on. In order to be able to do this concurrent assembling of or simultaneous assembling of several elements, we must reorder the elements in the form that all elements in the array have the same type and the same parameters in order to be able to perform the same operation of on all the elements that are currently loaded and that are currently processed. The big advantage of this cross-element vectorization is simplicity, and this approach is also the agnostic to element types and the length of the vector registers, because the way how the assembler is vectorized is not dependent on the element type. For example, we apply the same idea for vectorization of triangles. We apply the same idea for vectorization of hexahedrons and so on. We just load the more element at once and then run the computation, and the computation looks very similar to computation with just a single element. For implementation this cross-element vectorization, we compose this SIMD class. This SIMD class encapsulate vector data type and intrinsic function in the form that we create the struct with the internal data, and then we implement some load and store functions and all the operators. We overload all the operators that are needed to do in the assembler. Here is the simple SIMD class for working with the double only. But if we want to implement some vectorization, we just implement a second version of this SIMD class with the internal data that here are the internal data are two doubles stored in this class, and then all the loading, storing, and operators are implemented as the manipulation with the internal data with the vectorized instruction, and then we just use this SIMD class in the assembler. And in order to be able to support more type of vectorization, we must guard all the implementation with, for example, ifdef, in order to compiler be able to choose the correct implementation according to the supported in SIMD or intrinsics instruction set. In the assembler, all double values are substituted by our SIMD class, and it is the reason why the SIMD class must provide all functions that are used in the assembler, and it is, from my point of view, very simple substitution. Because the majority kernel functions stay unchanged. There is just a small exception for kernels for the functions that load the data, because during the loading, the data must be reorganized in the way, for example, that if you load a coordinate, you must put the all x coordinates together, then all y coordinates, and then the z coordinates, and so on. And also during the storing the data to the output matrices, you must respect this reorganization of the data within the assembler. This cross-element vectorization work very similar for all instruction set supported by the x86 architecture. In the SVE vectorization, it is the vectorization that is supported for AMD architecture. This vectorization is somehow different compared to, for example, AVX, because this type of vectorization introduced sizeless types, and these sizeless types cannot be directly used as SIMD class, because these sizeless types cannot be parameters of the classes. So it is not such a straightforward how to use this SV vectorization. Fortunately, there is a workaround, but the workaround is different for GCC and Fujitsu compiler, because GCC support this attribute that can create the data, even this data type is sizeless. With this attribute, the compiler create the type with the size, and this type can be used in our SIMD class. What is important, we must build the code with the following attribute, and then your code is not general to move your code to different ARM architecture with different length of the register, different length of the registers, but you must recompile your code for each size of the registers. In the case of Fujitsu compiler, the workaround is to use, for example, std array for internal data, and the SIMD class looks like in this example. In the case of GCC, we use typedef for this sizeless type with the attribute to provide the size of this data type. This data type with this attribute can be used in the SIMD class, and then we again overload all the functions that internally use the vectorized function for manipulating the internal SIMD data. In the case of Fujitsu compiler, we just use the type def for the same for the type with the same name, but it is internally used std array, and then again we use the vectorizate instruction for overloading the operators, and then the cross-element vectorization achieved a similar performance like with AVX instruction set and so on. So if we have this optimization already implemented, we can move to the second optimization, and it is the transformation of runtime conditions to compile time conditions. We use CPP templates for it, and by this metaprogramming, by this transformation of runtime conditions to compile time conditions, we allow the compiler to use to optimize the kernel, for example, with efficient loop unrolling or direct addressing of the multidimensional arrays. Because if the compiler knows the size of the arrays, it can pre-calculate the loading or storing the data from and to the array. And with this runtime, this compile time condition, we use the compiler to generate the code that is tailored for our particular parameters, such as element type and so on. So to implement this transformation, this metaprogramming optimization, we should divide the conditions inside the assembler to compile time conditions and runtime conditions. In our case, we implement as a compiler time conditions all the parameters that influence the memory footprint to improve the size of internal data, to improve the spatial locality of the data. And we also transform all conditions to compile time conditions for the parameters that influence loop counters. The rest of the parameters stay runtime conditions, such as physical parameters, turn off and on the boundary conditions, materials, and so on. So the first step of this optimization is the way how to transform the runtime conditions to compiler time. It is very easy because we can build following function. This function get runtime condition and evaluate this condition, and according to the evaluation, the particular compile time function is called with compile time parameter. For example, this compile time function is built by the compiler with the parameter evaluate to false and true. So there are two versions of this function, and according to these runtime parameters, we call a particular function that is needed in our current way. Of course, this runtime condition must be evaluated as small as possible. This optimization works very well with cross-element vectorization, because in the cross-element vectorization, as I said, we must reorder the elements in the way that we have a bunch of elements with the same parameters. So we are able to evaluate this runtime condition at the beginning of each set of the same elements, and then run this optimized version of the function for the whole set of elements without runtime branching. Then we must build the kernels. In our approach, we divide the whole assembler, the whole kernel into the subkernels, and these subkernels are again templated according with the parameters that influence the loop counters into the subkernels. For example, there is a subkernel with that is built for each element differently, because we template this subkernel with the nodes, Gauss points, and dimension. And then if the compiler compile this code, the compiler know the number of nodes, and it can apply loop unrolling for this branch, for this loop, and can improve the performance, for example, for the elements that have small number of nodes, and so on. If you look to our apply function, the apply function accepts the element, and this element is just a simple structure that contains all the data needed by the subkernels, by our assembler, to assemble the final element matrix. And as you can see, all the parameters are again of the type SIMD, so the data are prepared for this cross-element vectorization. In order to have this element structure as small as possible, we try to minimize the size of the parameters that are inside. It is the reason, for example, that this base function and derivative of base function are of the type double, in order to minimize the size, and the size is minimized in order to be able to keep this element in L1 or L2 caches. So in order to have very fast evaluation, very fast loading and storing data into this element. During the last step, if we have several subkernels that are optimized for elements and so on, we compose the element, the assembler from this highly optimized subkernels, and we use this element structure to exchanging data between these subkernels, and apply runtime branching or dynamic polymorphisms to call the subkernels that are needed to compose the final matrix. We experiment with two branching, with runtime branching and with the dynamic polymorphisms, because it is a different way how to pick the correct subkernels with different impact on the performance, and of course different impact on the complexity of the code. But the main idea of this dynamic selection is to build the whole assembler with the complexity that respect the complexity of computed physics. It means that if the physics is simple, then our assembler should be also simple and much faster than assemble for more complicated physics. This dynamic selection, of course, present some negative impact of the performance, but from our point of view, it is good trade-off between the simplicity to build the kernel from the simple subkernels, and to get this dynamic behavior, the adaptation of our assembler to a particular physics. As I will show you in the measurement section of my presentation, for example, this runtime branching is very effective because the hardware contains branch predictor, and because the the reorganization of the elements to have the elements with the same parameters on array. These branches are evaluated always the same, and branch predictor minimize the negative effect on the performance. So in the case of runtime branching, the whole kernel can be following. We call our loop of on the bunch of the elements with the templated parameters, and then we create element structure on the stack in order to again improve the performance. This element structure is again templated, and then this element is used in the subkernels that are again composed in the loop function in the whole assembler, and then these subkernels are called in the hot loop, and according to the parameter if the subkernel is active or not, we call the apply function. So we call the subkernel that performs some computation, because this runtime branching, these if statements are evaluated always to the same value. It is very fast, and even the subkernels and the branching is in the hot loop. It works very well. The second version of our kernel is with the dynamic polymorphisms. In this version of the kernel, we get on the input the vector of subkernels that should be called for the particle of physics. Again, we create the element on the stack, and then we pick all active kernels, and these active kernels are the only kernels that are called in the hot loop. So we try to minimize the number of subkernels that must be called in the hot loop. For example, it is very easy to apply optimization for constness. For example, if we have some kernel that is evaluated for all the elements the same, we can evaluate this kernel only once at the beginning of the application, and then in the hot loop we evaluate only the kernels that are different for each element. So in this way, we can build the whole kernel that is composed from the highly optimized subkernels. Of course, the disadvantage of this approach is that this calling of apply function is that there is dynamic polymorphism. So in this way, the compiler cannot inline the function. There must be some overhead of this dynamic polymorphisms. So with respect to the performance, we measure our kernel on IT4I clusters, Carolina and Barbara, with Intel and GCC compilers, and we tested it in our tool ESPRESO that is publicly available on GitHub. Carolina is the cluster with two types of nodes with the AMD CPU, and both CPUs support AVX2, so we evaluate 4 elements at once. In the case of Barbara, there are also two types of node with Intel CPUs, and these CPUs support evaluation of 8 elements at once. We tested our assembler with the assembler of heat transfer. It means that with the heat transfer, we have the physics that has a 1 degree of freedom per mesh element. And we test our approach with different 2D and 3D tasks, with increasing the complexity and with different type of elements, and with polynomial degree 1 and 2. And we always run the assembler with the following number of elements. The number of elements was set in order to run the assembler at least half a second, and in order to data will be larger than the size of L3 cache in order to avoid some caching. So in order to get the performance of the real models. So at the beginning, we have evaluated the effect of cross-element vectorization. Here is the comparison of the kernel with cross-element vectorization over auto-vectorized code. The auto-vectorization was implemented in the form of SIMD class with the double value for internal data. And in the case of the Intel, we see that the improvements of cross-element vectorization, the speed up is between 4 and 6. And it is significant speed up. It is not the theoretical limit that is in the case of Intel, the limit is 8. It is the reason why the speed up is not 8 is that the speed up is between the cross element and auto vectorized code. So it means that the baseline is the assembler, the baseline assembler can contain some vectorized function already. We see that even we test the cross-element vectorization with two different examples, 3D example 0 and 3D example 4. The behavior, the speed up is very similar. In the case of AMD, in the case of Carolina, we see that the speed up of with the Intel compiler is above the theoretical limit that is 4 in the case of AMD. The reason is that the auto vectorization is very poor with Intel compiler on AMD CPUs. So we see that auto vectorization the code with auto vectorization is worse than the simple scalar code. But with this cross element vectorization, the performance is expected. So if we have this cross-element vectorization, we can apply the second step of our optimization, and it is the metaprogramming. Here we can see the performance, the relative speed up of kernels generated by metaprogramming over the code with runtime parameters only. So the speed up is between the code that the compiler know the number of nodes, GPA, Gauss point, and so on, compared to code that the number of nodes is unknown for the compiler. We see that the speed up for Intel architecture, Intel CPU is significant. On average, there was around 30% of speed up for all tested tasks. In the case of AMD, there were tasks that the performance with the compile time parameters were worse. But on average, the speed up was about 7% on the top of the cross-element vectorization. So this metaprogramming optimization is also beneficial for the performance. and it is easily to apply. So we recommend to apply this type of optimization together with cross-element vectorization. In the next figures, we compare the performance of our dynamic selection of the kernels. We see three pictures with different set of elements. The leftmost picture contains 2D elements and 2D task. The middle picture show the 3D elements, the linear elements, and the rightmost picture show the quadratic elements, so the most computation demands, the elements with the most computation demands. Again, because we test the several tasks with increasing the complexity, we see that the best, the slowest time for evaluation a single element is the lower for the more the most simple tasks that are on the left side. With the increasing the complexity, with the increasing the number of tasks, the time for evaluation of a single element is increasing because there are more computations that are needed to do in the assembler. For example, if we compare task 3D0 and 3D6, the 3D0 is a task with the isotropic conductivity. In this assembler, some operation with the matrices can be done just with the scalar. So the assembler is very simple. If we compare this task with task 3D6 with the advection diffusion, where we must evaluate the whole matrices, and the matrices are asymmetrics, then the observed maximal speed up between these two tasks was almost 3. So we see that there is a significant improving of the performance if we adapt the kernel for the particular physics. I also want to mention the last task, the task 7 and 8. This task contains trigonometric functions like a sinus, cosinus, and so on. And if we evaluate this function inside the kernel, the time for evaluation the kernels significantly increase. But here we can apply another type of optimization, and it is the recalculation, pre-calculation of the trigonometric function before the kernel, and then if we run the kernel with the pre-computed values, then the performance, the time needed for evaluation, the element is comparable to other tasks without trigonometric functions. So according to this measurement, we state that the dynamic selection of the tasks of the subkernels can have significant and positive impact on the performance. Now we go through the overhead of dynamic selection. These pictures again compare the task with different complexity, from the simplest task on the left to the most complicated task on the right. And here we compare the kernel that was manually optimized with the kernels that use the runtime branching in the form of if statements, and the kernels that use the dynamic polymorphisms. We see that for the fastest kernels, the overhead of dynamic polymorphisms is big, but with increasing the complexity of the kernels, the overhead of dynamic polymorphisms is very small, and what is important that the performance of runtime branching is very often identical to manually optimized kernels. If we show the relative performance between the manual kernels that are used as a baseline for this measurement, we see that even there is a big performance penalty for dynamic polymorphisms for runtime branching in the form of if statements. The observed penalty for this if statement was up to 14%. So if you want to build your assembler with very small overhead, the if statements are a very good option for how to implement this runtime branching. Here we compare the absolute performance of our kernel on the roofline model, so we can see if we reach the peak performance of a particular kernel or not. We see that in the case of AMD, we reach the 10 from 10 to 20% of the peak performance for the simplest kernels for 2D elements. In the case of Intel CPU, we reach the performance from 10 to 30%. That is not the peak performance, but if we compare the performance of the 3D examples with, for example, anisotropic conductivity, it is the example where the full matrix must be evaluated for implementation of the conductivity. Then the absolute performance in the roofline is higher. We achieve from 20 to 50% of the peak performance, and it is comparable with the performance that were achieved by other researcher. And this performance of other approach is showed by this gray rectangles. So you can see that the performance is almost similar for other approaches. The reason why the kernels don't have the peak performance is that the kernels are memory bound. If we use the element with a higher polynomial degree or some more complex physics, then the performance would be higher, would be better. But this performance is typical for this type of assembler. So here we have a slide with comparison our kernels on real-world example. Here we have temperature sensor. The majority of materials in this sensors in this sensor are isotropic, but there are small portions of materials with anisotropic behavior. So the material that is more complex to assemble. And if we test this, our adaptation, our dynamic selection of the kernels on this sensor with the linear elements and with the quadratic elements, we can see that there is high impact of cross-element vectorization if we compare the time for assembling the auto-vectorized code and the code with the cross-element vectorization. There is again significant speed up. What is also important that if you, for example, compare different compilers with the auto-vectorization, we can get very different time for evaluation. So the time is almost random. If you can significantly speed up the computation just with the change the compiler. That is not good behavior that you want to achieve. But with the cross-element vectorization, the performance, the time for computation is very similar. So it means that the cross-element vectorization works very well independently on compiler. If we compare the speed up achieved by the adaptation, we can observe that the adaptation of this linear model speed the computation up to 11%. In the case of the quadratic model, the computation, the assembling of this sensor was speed up to 25%. That are the numbers that are similar to the numbers that we achieve on the artificial examples that was presented in the previous slides. So as a conclusion, I can state that our approach is very flexible because by the straightforward code modification of the original scalar code, you can get the vectorized assembler with near optimal performance. And according to the complexity of the subkernel, you can choose between the runtime branching or dynamic polymorphisms. For example, in the ESPRESO, in our tool, we use runtime branching for selecting boundary conditions and so on. And we use the dynamic polymorphisms for evaluation of external expression defined by the user, because in many cases these expressions can be are constant, so we can call this evaluation just once, and it is very simple to implement it with dynamic polymorphisms. Here is the maximal performance penalty for runtime branching. So it was 14% at maximal, but the average performance degradation was up to 2%. In the case of dynamic polymorphisms, the average degradation was about 30%. Even the maximal performance degradation is much higher. It is just for the fastest kernel, for the simplest one, and we can see that the maximal performance degradation is always smaller than the maximal speed up that was achieved by the dynamic selection of the kernel. If you want if you know more details about our approach, I recommend that to read our paper and check the implementation in our tool ESPRESO. Now I thank you for your attention, and I will be happy to answer your questions.
Thank you. Thank you for this presentation. So we are running a bit late, but do we have questions?
Yes, hello.
Yes, please go ahead.
So you talked about vectorization, which is only single core.
Yeah.
Do you have parallelization implemented, and how do you do this?
Yes, this implementation is the approach that I describe is just for the single core, but you can run you can just implement the parallelization by the single loop with OpenMP. If, for example, in our approach in the ESPRESO, the solver is based on domain decomposition method. In this way, we can run assembler for each domain separately. So if we insert the element matrix into the global matrix, this global matrix is decomposed into the domain. So we avoid race condition by inserting the elements into the separated domain. If you want to build just the simple matrix, you can avoid the race condition during the inserting the kernels into the whole matrix by the graph coloring, in the way that if you color your finite mesh by the colors in the way that there are no elements with the same color that share the same nodes, then you can run your assembler in parallel for all elements with the same color, and then it is assured that even the several threads insert the data into the final matrix, they insert the data always to different locations, so the race conditions are avoided by this graph coloring approach.
Thank you.
Okay, interesting. Thank you.
Any other question in the chat or no? No other question? You sure? Okay. So I would like to thank our speaker. Thank you very much for this detailed presentation. I'm not going to say I hope to talk to you next time in April, because this was my last EUPEX webinar. I'm retiring in 2 days exactly, on Friday. So next time the EUPEX webinar will be run by my colleague Pelagie. She was not able to join today because she's in the train currently. We are going to work together this afternoon. So I would like to thank everyone, and thank you all for attending those webinars. I hope you'll have many more successful EUPEX webinars. So remember, 9th of April, webinar on Ocean, on CA's Ocean. Please register, and I will send the link actually together with the today's slides. So thank you again. Thank you to our speaker. Thank you to our audience. Bye-bye.
Thank you. Bye.
Bye-bye.